Okay, lecture 3 of the scary mathematics. We continue exploring response functions of linear time invariant systems, and today is mostly about examples and methodology. We will go through a few practical tricks that in the Laplace domain make it a bit easier to handle differential equations, and we will also prove a few statements about asymptotics. So the final value theorem, the initial value theorem, and a bunch of examples thereof to top of the lecture. Okay, so item 1 is the asymptotics. Consider situations where you would rather not solve the full system of differential equations that you have. You only want two things. Firstly, to find out whether a system has a steady state under a particular input, and secondly, what that steady state might be. So, final value theorem. And there are two aspects to this. One is that a lot of systems simply wouldn't have a steady state. If you are continuously driving something with a sinusoidal input, of course there will be sinusoidal dynamics in the system, and if the input does not cease, then that dynamics would likewise continue oscillating, and so there will be no limit because the system never settles down. But if we do have an input which is static, for example, the step function, it goes up and then continues, then perhaps there will be a steady state for the system. And so our task now is to firstly to prove the theorem, and secondly to establish the validity conditions for that theorem and for whether there is a steady state. So first, the statement: if we are looking for a steady state of a system, if it exists, it's the limit of t going to infinity of y of t, so of some output of our linear time invariant system, and it is equal to the limit s going to 0 in the Laplace domain of s times the Laplace image of the output of the system. So a bit obscure, as you can see, so let us go and prove it from just the statement. So proof, and the proof would also inform us about the validity conditions there. So let us start with this limit. So we have the limit s going to 0 of s y of s. Let us ask ourselves, where have we seen something like this before? It was, of course, the derivative property of the Laplace transform. Remember that L acting on f prime of t was s f s minus f of 0. So you can see this thing here. So what I will do is I will take this and I will substitute that here. So in the outer brackets here, we would then have the Laplace transform of a derivative of y, and if I shift that over there, there will be plus the initial value. Check there's a typo in equation 2 of the handout. It should be a plus, not a minus there. Okay, so a limit of s going to 0 of then this Laplace transform, so L of y prime of t, and then plus y of 0. Okay, we made some progress. Let us now substitute explicitly here the Laplace transform of y prime. So still the limit of s going to 0, but now of an integral from 0 to infinity y prime of t e minus ts dt. So that is the Laplace transform of the derivative, still plus the initial condition, y of 0. Okay, let us pull the limit in. Remember what we knew about the limits. If we have the limit of a sum where the limits of the two terms individually exist, then that is equal to the sum of the limits. And then if the integral is sufficiently well behaved, I will not go into the detailed conditions because we don't have the time in this module, but you can swap the order between the limit and the integration, subject to certain conditions of this function, which we assume are satisfied. Okay, so what that tells us then is we have an integral from 0 to infinity. Limit is with respect to s, so it's just pertaining to that exponential. We have y prime of t, then the limit of s going to 0 of e minus ts, then dt. And of course this doesn't even depend on s, and so the limit of that number is simply equal to the number itself, y of 0. Okay, but of course this limit trivially exists. If we put s to 0, this entire exponential is equal to 1. And so we have an integral from 0 to infinity y prime of t dt plus y of 0. The integral here is again trivially taken, right? The integral of y prime is y itself. Remember the definition of an infinity integral like that. It is the limit with respect to parameter going to infinity. So here we have the limit y of t going to infinity. That's the upper limit of that integral. The lower limit is y of 0 plus y of 0. These two trivially cancel, and we do have the other side of our original statement here. So we have proven it backwards. We have started from the right-hand side, and we have arrived at the left-hand side. Let us now think about the validity conditions here. Firstly, all of the Laplace transforms in question and all of the limits must exist. Secondly, we are in the Laplace domain, so in the right-hand side here, sy of s, we must be careful that none of this inverse Laplace transforms into an oscillatory function, because an oscillatory function with no decay term on it never settles down and becomes stationary. So we must have applicability conditions. So applicability. So A, all limits exist. B, all Laplace transforms exist. And finally, an interesting condition. Let us take a look at the typical structure of y of s. It is usually a rational expression with polynomials in the numerator and the denominator. So y of s is some polynomial of s here and some other polynomial of s there. What did we have here when we transformed all our typical response functions? Remember that all our equations were LTI, so linear time invariant differential equations, and the solutions for those, because they are linear with respect to all of the derivatives involved, they are linear combinations of exponentials. So y of t was some alpha 1 e lambda 1 t plus alpha 2 e lambda 2 t, and so on. And all solutions have this type. When is a solution like that oscillatory? It is oscillatory when lambda contains an imaginary component, when this is not a pure real number. So let us take a closer look at it. It's e alpha plus beta I t, where the beta part will go into the sine and the cosine as per the Euler's formula, and alpha will be either the rising term or the decaying term, depending on the sign. And so for this to settle down into something, we must firstly not have it rising indefinitely, so alpha must be less than 0. And secondly, we must have beta that is not just oscillating, right? So it is actually decaying as well. So that, in fact, is the necessary condition. And so if we look at the complex plane, we have here the alphas and here the betas. Let us consider the 4 quarter planes here and decide what we don't like. If alpha is positive, this exponential will blow out into infinity, possibly in an oscillatory way, so no limit. Okay, so positive alphas are out of the question. So that is forbidden. Then let's take a look at the 0 alphas. If alpha is 0, then that keeps on oscillating unless beta is 0 too. So the vertical axis is also off limits. So these points are shaded. So in essence, we must have a decaying exponential. And so finally, the third condition. So see that the denominator of this polynomial, which is what is responsible for these lambdas, must not have any roots in the right half plane. Strict mathematical formulation of that: no poles of y of s in the right half plane. Which is a bit of a technical condition. Essentially, what this physically says is there should be no unbounded rises or oscillations in the function. Everything must decay and fade asymptotically to something fixed. And under that circumstance, the final value theorem applies, and we can get the steady state. There is its mirror image. If you swap around the time and the Laplace domain, there is the initial value theorem. So symmetrically, the limit of time going to 0 of y of t is the limit of s going to infinity of s y s. So notice now this goes to 0 and that goes to infinity, proven in a similar way, so I will not bore you with another rendering of that with similar conditions. Sometimes it's not actually necessary to go through this entire Laplace exercise, because the very definition of the steady state is that all derivatives are 0, because nothing's changing anymore. And in a lot of cases, you can find out the steady state from just the time domain differential equation by putting all of the derivatives to 0, and then you've got an algebraic equation for the steady state. So let's go through an example of that. So example, we'll do it this way, and then we will do it by the method of staring and experience. And that is when you cut corners, because you can actually read into the dynamics that you are looking at beyond the equation that describes it. Okay, we have a system d2y by dt plus 3y dy by dt plus 2y of t. And as an input, we have the Heaviside step function. And we are asked, firstly, to determine whether a steady state exists here, and secondly, to find that steady state using the final value theorem for the Laplace transform. And we are told that these are either deviation variables or we have a genuine 0 initial condition. So that is our initial condition, which then goes into the differentiation theorem for the Laplace transform, and we get it in. Fine, so the first thing we do is we apply the Laplace transform to both sides of the equation. So we have s squared y of s plus 3sy of s plus 2y of s, and the Laplace transform of the unit step function is the standard thing that we have derived in the previous lectures, so 1 over s. Nice and algebraic in the Laplace domain. Let us solve this for y. So y of s is 1 over s, then 1 over s squared plus 3s plus 2. This is the Laplace image of our solution. You can see the transfer function is being multiplied by the Laplace image of the input, so exactly the same formalism as we have seen in the previous lecture. Okay, so let us now firstly check that we have no roots in here in the wrong place, and secondly we do the limit. All right, that's a quadratic equation. Let's find out what the roots are. Do I have them in the handout? No, so let's do it the long way. Okay, so we have a half. Let us now obtain the same half by the method of careful staring. If we look at the original differential equation over there, we know what the step function is. It initially rises and then it stabilizes. It keeps on going. So this is clearly stationary. And should a steady state exist, it is of course a state at which y no longer changes. And so we are going to have this derivative here going to 0, that derivative there going to 0, this step function becoming equal to 1, and so at the steady state 2y equals 1, and therefore y is equal to half, right? This is a more physically motivated way of doing that than the Laplace transform, but notice how the Laplace transform is a lot more computer friendly, right? We are here relying on physical intuition. We are not, strictly speaking, even checking the poles of the polynomial that turns up. We are just hand waving. A computer, of course, needs to know all of these coefficients. It will internally run the roots of that polynomial, compare them to the conditions that have been specified, and then it is going to produce us the answer. So there is, yes?
So if you did that question and then you worked out the roots, and one of them was in the right-hand side, would it not be able to?
Yeah, so what's going to happen then is there will be, so if we write that out, the inverse Laplace transform would look something like that. It would be e minus lambda 1t with some coefficient alpha 1 plus alpha 2 e lambda 2t. So the situation you describe corresponds to this. If lambda 1 and lambda 2 are positive, then this, and maybe plus lambda 3. So this would fade when t goes to infinity and just disappear. However, if lambda 2 is positive, if it is sitting in the positive half plane, that exponential is going to explode, right? And of course, then the limit doesn't exist. However, if they are both negative, they will both disappear. We are left with lambda 3. And in this case, the lambda 3 happens to be equal to a half. So it might decay to something, it might ascend to something, it might wobble down to something, but there has to be a decay in the system which corresponds to the roots sitting in the negative half plane. If there is no decay, there is no limit. Okay, so that was the final value theorem, and now we go on to practical response illustrations. So item 2, response library. And input library. And this really relies on the examples that I have given you in the 2 previous lectures. We can have in engineering a variety of standard inputs. They are not necessarily standard in the sense that that's the input that you see, more often not, but they are the kind of inputs out of which most other inputs may be built. So if you take a linear combination of those with some amplitudes, some delay factors, some multipliers, essentially any other input can be built as such a combination. So the first one is step of amplitude A, and that is the one that we've seen there already. If we have here, that's time, then nothing happens in the negative time period, then it goes up to amplitude A, and it keeps on going indefinitely. So some source has been switched and some substance started arriving into the reactor, and it will keep arriving in perpetuity. Okay, so the mathematical formulation of that is the input x of t is a piecewise defined function. It is 0 for t less than 0, and it is equal to a for t greater or equal to 0. Now, there are various ways of putting this less and greater or equal. They are all cosmetically different, but actually equivalent, because if you go through the mathematics of integrations, then changing function in just one point does not actually change its integral. And so, various combinations can be seen in the literature of what is less and what is greater or equal there. And of course, you have seen the Laplace transform of that already. I have done it in one of the previous lectures, A over S, and that is the one we have used here when we have dealt with our steady state. So, B ramp with slope small a. And this is one of those situations where, engineering and stability and the roots in here might start playing up, because of course we cannot ramp something up indefinitely. At some point we run across the pesky physics where stuff cannot be infinite, but that is our slope a there, and that is the input. So we have x of t, again 0 initially, and then starts ramping up, 0 for t less than 0, and at for t greater or equal to 0. Those of you who have done a little bit of artificial intelligence by now will recognize the ReLU activation function. This is actually one of the applications of what you are dealing with. In a lot of cases, layers of artificial neural networks follow exactly the same mathematics as the one you are seeing here. Okay, that is the ramp, and once again, the Laplace transform was given in the previous lecture. T will necessitate a round of integration by parts, but if you watch the video from that day, I have actually done it. So A over S squared here. The third important class of inputs are oscillatory ones. For the chemical engineering, you don't see them so much because it's not very common for your concentration or your flow rate to be an oscillating function of time, but they are of course all over the place in electrical engineering, where you have oscillatory radio frequency or microwave signals in the circuits, for example. So see here, monochromatic wave. Monochromatic meaning single frequency, but also we of course must have it 0 before the time started, and then it becomes non-zero. So x of t, if it's a cos then it's 0 for time less than 0, and then amplitude cosine omega t for t greater or equal to 0, or if we have a sine, so that is 0 for t less than 0, and a sine omega t, t greater or equal to 0. Electrical engineers have no problem with complex numbers, and in a lot of cases you will simply see a complex exponential input, of which the real part is the cos and the imaginary part is the sine. That is a way of doing it simultaneously, and it's also friendlier to the version of these transformations that electricians like rather more than Laplace transform. I don't know if you've come across Fourier transform at some point. It must have been mentioned to you. In those cases, Fourier transform is actually preferable over Laplace transform because it is easily numerically invertible. Right? Laplace transform inversion is numerically unstable, and it's actually one of the biggest tragedies of the Laplace transform. Okay, so in this case, x of s, and we will be using all of this, so I'm writing them here. A omega over omega squared plus s squared, and in here x of s is as omega squared plus s squared. Okay, now the final thing, item D, here is a square pulse. In the limit of infinitely short widths, but still finite power, it becomes a delta function, and we will see an example of that. So in this case, it is 3 pieces. It is 0 when time was less than 0. It has some amplitude when the time is greater than 0, but less than some widths. And I should be careful to write a W here rather than the omega, and then it goes back to 0 when t is greater or equal to that width. So nothing was happening during the negative times. Then we have amplitude A for duration W, and then it goes back to 0 again. Now, what is important about all of these, and you will see examples of that if you look through the chapters that I've suggested that you read in this handout, just about any function, just about any input can be reasonably well approximated by a combination of that, and this, variously shifted and truncated. You know, whatever particular input you have. So to give you a simple example of that, so if you have some continuous input into your system, well, we can simply just cut it up into pieces and say that approximately, actually, that first piece is a combination of the square pulse with a little bit of a linear ramp on top. Then likewise for this, except it's also shifted and the ramp is in the negative direction in this case, and so on. So a combination of shifted pulses, ramps, and steps can approximate to a fair degree, particularly if you make these slices finer, just about anything you can realistically put into your system, which is why these fundamental inputs and the fundamental responses to those inputs are important. Okay, let us go now through our response library, and today we will only look at first order processes, so those where the function in the denominator of the transfer kernel is linear. So we consider systems that are first order. And we know that for a first order system, first order of course refers to the differential equation that's describing it. It can always be written like that: k over tau s plus 1 times the Laplace image of the input in the displacement representation of it. K is called the amplification coefficient, tau is called the time constant of the system, and we will see in a few moments what exactly is meant by them when we start looking at the various responses. So let's plonk a step input into that system and take a look at what the output is going to be. So a step input. Okay, we pluck out our Laplace transform of the step input. There it is. And therefore the output is going to be that. So it is k over tau s plus 1 times a over s. Well, we have a product, and our book, which contains a giant collection of Laplace transforms, might not have a direct entry for such a combination, but it does have an entry for 1 over ts plus 1 and 1 over s individually. So we need to do partial fraction expansion here, the same A-levels mathematics that you've probably been bored stiff with at school. And so we have two coefficients here, let's call them alpha over tau s plus 1 plus beta over s. And let us find out what those coefficients are. So we do that by just bringing it again over the common denominator. So we will have alpha s plus beta tau s plus 1, and that is tau s plus 1 times s. We open up the numerator and equate the terms with and without the s. So we have with s it's alpha plus beta tau s, and without the s it's just the beta over the denominator tau s plus 1 times s. Now, notice that this must be true for any value of s. And we have denominators that are equal, so Ka must be equal to alpha plus beta tau s plus beta for any s. Well, of course, the only way that's possible is if that term is 0 and beta is equal to Ka. And so our outcome as the result of that, so we come out of here, is then Ka over s minus the result of this being 0. So beta is equal to 1, well, beta is equal to Ka, and alpha plus beta tau is equal to 0, and it follows that alpha is minus Ka tau. So in here, Ka tau over 1 plus tau s. Okay, and for this, of course, we know our inverse Laplace transforms. This is a constant, and that is the exponential. And so back into the time domain, we have y of t equals Ka1 minus e minus t over tau. And this explains the names for the amplification coefficient and the time constant. The input is plainly equal to a, right? When the time has been turned on, the ramp becomes equal to a. Notice what happened to that input. It got multiplied by the amplification coefficient, so amplified or suppressed, in fact, if k is less than 1. And then the system needs some time to settle. Initially, there will be some dynamics in it, so there will be some initial condition here, Ka, and there will be this negative term which will get itself subtracted. So if we plot this as a function of time, so this is y of t and that is the input. Initially, when time is 0, we start at 0 because the bracket is 0, and then it rises exponentially and asymptotically approaches the value that is the amplified input value, so Ka. Ka. And the time constant here is tau, right? That is the first order time that it takes to get there. Okay, so it got amplified by K, and the response time, the characteristic time of the system responding to that change, is tau. If we then suddenly switch A down, right, so for example to a different level, like here, B, then what will happen is the system from here will go down to the new level, again exponentially with the time constant tau. So the characteristic time of the system is that quantity. All right, this was the response to the step input. Let us take a look at the response to the ramp. And there we have to be careful because a ramp cannot continue to infinity because it would become infinite itself. So we have to be cognizant of the fact that that is, of course, an approximation that is only likely in any physical real system to be applicable at finite times, and probably not terribly long times because the ramp keeps ramping up as it goes. It will be a bit more complicated now because the Laplace transform of a ramp has an s squared in the denominator, so I do hope you remember the corresponding trick of the partial fraction expansion, again from your A levels or further math or whatever it was, maybe kindergarten in certain countries, and let us do that. So B ramp response. Well, we look it up in our big library of inputs. That's A over S squared. So as a result, we have Y of S is A over S squared times the transfer function, same transfer function that we've agreed to use at the very beginning. So K over tau S plus 1. And this is again a partial fraction expansion, except now there will be 3 terms. There will be a term with 1 over tau S plus 1 in the denominator, a term with 1 over S squared, and a term with 1 over S. And that is the thing that I hope you remember from your exercises in that. I will not bore you again with the process of finding those coefficients. This is Ka tau squared over tau S plus 1 plus, or rather minus, Ka tau over S and plus Ka over S squared. The inverse Laplace transform, these individually are there. You can see that that's the exponential, that's a constant, and that's a ramp. So of t will be Ka tau over e minus t over tau minus 1 plus Ka tau, Kat. And this is one of those cases where the steady state doesn't exist. If you go through the roots of that polynomial, you will see that one of them is sitting, if memory serves, not in the negative, but on the actual vertical axis. And this t, of course, if time goes to 0, will blow up the entire system. But notice what is happening here. If we start plotting this, this will now have not an asymptotic value, but an asymptotic solution. So if that's time, and that's y of t, well, if time goes to a serious infinity, right, so y for t that is much bigger than tau, Let's think about what it's going to be. When t is much bigger than tau, this exponential has a very large index. Because the index occurs with the minus sign, the entire exponential goes to 0. So we only have the minus 1 here. So this is going to be k, a, and then t minus tau. So we have shifted our input in time by tau, and we have amplified it with the amplification coefficient. So here, let's say if that was our input, right, so that's x of t equals at. Then our system will probably not amplify, it's more often that it is damped, will firstly damp it by k, so this is k a t, but secondly it will also shift it by tau, so there will be a shifted value where that distance is tau. Secondly, we will only have it on this line for t's which are large. So somewhere here is when that is going to happen. But of course our initial conditions are 0, so we must begin here. And there is an exponential crossfade between this 0 and the asymptotics. So notice what happens at time 0. This term disappears. This exponential becomes 1. 1 minus 1, 0, so the initial condition is 0. Then the eventual asymptotic is here, and so what we are going to have is an exponential crossfade towards this asymptotic. It will slowly approach it, again with the time constant tau. So that is the dynamics that we are going to see in that system. So this is our y of t in blue here. Right, let us briefly go through the monochromatic wave response. It's not terribly relevant to you chemical engineers, but what I am going to show you is generally a similar picture to this, except for a wave. So see, wave input. You've seen the Laplace transform of the cosine and the sine. Let us put a cos into there, do the math, it's in your handout, and then y of t after the dust has settled looks like this. It is ka omega tau over omega squared tau squared plus 1 e minus t over tau plus ka over root omega squared tau squared plus 1, and then sine omega t minus phi, where phi is an arctangent of omega tau. So quite a lot to take in, and so far so obscure, but let us take a look at the just outside features of this solution. Of course it takes 20 minutes of dense mathematics to even obtain. Firstly, the amplification coefficient is still overall, right? Our solution is multiplied by k, and it does not occur anywhere else. So indeed k is again the amplifier. Secondly, there is some seriously complicated dependence on omega and tau. These are resonance conditions of the system. You will see them if you ever do nuclear magnetic resonance as chemists. I will again not go through it, but the pertinent thing about the rest of this solution is notice that this decays. This decays with the time constant tau and will eventually go to 0 when t is much bigger than tau. That thing keeps on oscillating, and so this will not in fact have a steady state as we previously observed, but it still has the sine wave which has been delayed by a time which is the function of both the frequency and the response time. And this is the pattern that you will see time and again in your systems when an input goes in. Two things happen, well, three things happen: amplification, crossfade, and delay. And this is something you will be looking for in a lot of cases when you deal with these systems. And I think that's pretty much what I wanted to say. We move to the workshop questions now. You have the answers at the back of your handout. Mathematica produced them. Any questions?